Hi everyone, and welcome back to the third lab of the cloud computing course. I'm Marco Iorio, and in this video we will see how we can leverage Kubernetes to run simple applications. So here on the right you can see my terminal, which is already connected to the control plane node of the cluster we created previously. We can see the cluster is composed of 3 nodes, 1 control plane and 2 worker nodes, which will be used to execute and to host our applications. Let's start by exploring our cluster, and the first thing we can see are the namespaces. So we can do k or kubectl get namespaces, ns for short. And here we see the list of namespaces in our clusters. Namespaces are abstractions which are used to group together related objects, such as pods, deployments, services, configurations, secrets, and so on. We can see 3 namespaces which are used by Kubernetes for its own control plane objects. And we can see the default namespace, which, as the name says, contains is used as the default when another namespace is not specified. Second, we can explore the pods that are running in our cluster, and we can do kget pod. We see that no pods are currently running in the default namespace since we didn't start any application yet. But we can do kget po minus uppercase a, which shows all the namespaces, and we can also do minus o wide, which introduces additional information. And we can see there are different pods which are running in the kube system namespace, and those are the pods that are required by the control plane, so the ones we saw previously. Okay, so we are ready to start deploying our first application. We will start with a stateless application, an Nginx server, which does not require any persistent storage to be maintained. So those applications are the easiest to execute and are perfectly compatible with the Kubernetes abstractions, as those can be stopped, restored, for instance, upon a failure on a different node with no problem. We can scale them to multiple replicas and so on. We have different ways to start an application, and we typically leverage the deployment abstraction, which explains, which configures our desired configuration in Kubernetes. And we can either imperatively create a deployment through kubectl create deployment and all the set of parameters, or we can use YAML files to express a declarative configuration. The advantage of the declarative configuration is that we can store those files, for instance, in a Git repository, for later use, so we can know which is our desired state. So here let me open the file, so deployment Nginx. This is exactly the same YAML file you see here on the left. Pay attention that YAML files rely on indentation for their correctness. So when copying them, it is necessary to pay attention not to scramble tabs with spaces and so on. And this is especially true if you copy them from the PDF. So more in detail, we have here a deployment which is associated, which uses a template with the Nginx with this tag image. So it says, okay, I want you to create some pods characterized by this template, and in particular with this container, and we want exactly two pods to be started. So we can create our deployment and apply our configuration through kubectl apply -f and then the name of the file, so deployment Nginx. and we see the deployment has been created. Now we can inspect our deployment. We can do kget deploy, and we see that we have 2 replicas desired and 2 of them are already ready. We can also inspect the pods, and we see that effectively we have 2 pods which are running. We see here on the left that the matching aspect between the deployment and the pods is this selector. So this deployment is controlling all the pods which are characterized by a given label, and we can see here the pods are labeled with the up equal to nginx label. We can inspect further our deployment, so we can do kubectl describe deployment and then the name nginx, and we see here some more information about our deployment, the number of replicas, the selector I was previously talking about, the information about the container, and the current status. So it's saying, okay, everything is fine, it is available, and so we have 2 replicas. And the nice aspect in Kubernetes is that we can rely on these high-level abstractions to express our desired state, and then Kubernetes will take care of applying this configuration and maintaining it true. So let's open a second terminal so that we can just see how the state of our cluster evolves, and then start watching our pods. I will do kubectl get po -w watch, which keeps a stream and keeps displaying the events that affect our pods. So let me insert a space so we can better see what happens. And then now on a second terminal, let's delete the previous pod, one of the 2 replicas. So here we can delete the pod either by mistake, let's say an administrator is doing something wrong, or because the pod is not working correctly, or even because the node is not working correctly, and so it's no longer capable to host our pods. So when we delete our pod, we can see that one pod has that pod has started terminating, but immediately Kubernetes has created a second pod to replace our previous one. And so if we again do kubectl get po, we see we have 2 pods, one which is younger than the other since it has been created as a replacement. So here you can see the effect of the control plane loops of Kubernetes. We have the deployment which says I want 2 replicas, and then Kubernetes does everything to effectively create and make 2 replicas of the deployment run. It does so through also an intermediate abstraction, which is the replica set, which sits between the deployment and the pods. So here we have started our first deployment. We can do different things with the deployments, and here I open again the stream to see the events. And then what I can do, for instance, is to scale our deployment. So kubectl scale deployment, the name of the deployment, and the number of replicas. Let's say I now want 5 replicas. I can change this value, and immediately Kubernetes scales our deployment to 5. I can set it to 1, and it immediately starts terminating 4 replicas, so that we have only 1 running once more. So it's a bit harder to see, but if we do so, we can see we have only 1 more replica. So those are just some of the aspects that the deployments can manage. They can also deployment rolling updates, and so they take care of the changes, so that when we, for instance, want to change to update the image, they take care of updating one pod at a time, so that we can be sure that if the configuration is wrong, only that pod is affected, and if we have multiple replicas, we can continue to serve traffic. We don't have any instant in which we are no longer able to serve traffic. So let me just have a look what the lab suggests to do next. Okay, so let me scale once more, let's say to 3 replicas. So we have some replicas as a backend. And now what we can do is to create a service. We want to create a service so that we can use it as an abstraction to access our replica, our backend pods, but we don't want to target specifically one pod. As you can see, those can be destroyed and recreated at any time. But we want a higher level abstraction, something in front that remains stable. So once more, we can create a service through its definition. We create here a service which targets again our pods through the selector. The selector pattern is something that is widely used in Kubernetes, and we say we want to expose those pods, and in particular they port 80 through a port 80. We create here a service of type cluster IP. Cluster IP means that this service will use private IP addresses that are reachable only within the cluster. So we cannot use this service to access the backends, our application, from outside the cluster. There are different types of services. We can use node ports, as we will see just later on, which allow you to access an application using the IP address of any of the nodes of the cluster, both worker and control plane nodes, but using non-standard ports. So let's say 30, something, and so on. We have also load balancer and external service types. The load balancer is the one that is used typically to expose applications to outside the cluster, but the load balancer is something that is not implemented natively in Kubernetes, but it needs some external plugin which can either be installed, let's say, on premise. So MetaLB is one of the most widely adopted plugins, and instead on public clouds the load balancer IPs are provided directly by the Kubernetes provider. So we can apply our cluster IP service, again kapply -f, the name of the file, and we see that the service has been created. We can inspect this service. We see actually there are two services. Kubernetes is a service which is used to expose the API server within the cluster, so it's present in the default namespace and it cannot be removed. And then we have our Nginx service, the one we just created. We can describe it. So describe Nginx, and we see that it is associated with 3 endpoints. So those are actually the IPs of the pods that are running in our cluster. And once more, we can see if we scale the deployment, we can then inspect the service and see that the number of endpoints changed to account also that one. So now that we have the service, let me open it again. The service is associated with an IP address, and from within the cluster or from within any of the pods within the cluster, we can access this pod, this IP address. So we can do curl and then the IP address, and we see it is responding. One of the 4 now replicas of the application, one of the 4 random replicas of the application is responding to us. This is handled by a load balancer by Kubernetes. So Kubernetes is internally through kubeproxy load balancing between our replicas. If we run multiple times, here it is not printed which is the backend IP address, but we would see that those would change. So this is how services work. They provide an abstraction in front of our backend pods. We can also try something else. So we can run a pod. Let's run just an Alpine pod. Whatever is fine. So Alpine, we want it to run interactively, as we will use to interact with it, and we want to run bin sh, because Alpine doesn't include bash. So if okay, it worked. What we can see here is that if now I show the services, we can, as I was saying, I'm not using anymore curl, but get, since Alpine doesn't provide curl. I'm here within a pod, again in the cluster, and I can access the service. As you can see, it worked. I can also probably show the output with something like this. Yeah, it wrote the output, just as before. But the nice thing is that we can also rely on the DNS Discovery. So we can do, okay, I don't care about this IP, I just want to access that service. And I can do nginx, then default, then cluster, svc.cluster.local. And it should work. Indeed, it worked. We can also see with ns, let me copy it, so that we can use also ns lookup, and it should show, yeah, this is the address, which is actually the one here below. We can also probably use shortened forms, so typically also just name of the service, name of the namespace should work, and it did. So as you can see, services are a rather powerful abstraction to abstract the access to applications. Here we can also change our service to convert it into a node port. Once more, we can use the YAML file and then kubectl apply -f, the name of the file. So here we created our service. We changed our service to the node port type. Node port means that we can access this service from outside the cluster by leveraging the IP of any of the nodes. So I get now the IP of the nodes. I'm doing this still internally, since those IPs are not reachable from outside. You could access them from the management workstation, for instance. What I can do is to curl the IP of any node and then to the node port, this port which has been selected. So as you can see, again, we receive the response from our service. This is a way to access the service externally, but this is probably not the best one, as you can see, because we need to use these strange port numbers, which are not the best when you want to expose, let's say, an HTTP page or so. And for that, that is the reason why we typically use service load balancer types. So we reached the end for what concerns stateless applications. We can still go through how we can build and run stateful applications on Kubernetes. So let me delete the deploy nginx and then delete the service nginx. So we don't need them anymore. Now, so we want to run a stateful application. We want an application that requires a persistent storage to work, let's say a database. In Kubernetes, there are two abstractions which deal with storage, the persistent volume and the persistent volume claim. The persistent volume claim is tells that an application, a pod, wants to access a given piece of storage. The persistent volume represents that piece of storage, and it can be created either manually or to be dynamically provisioned by the controllers in the cluster when we create the persistent volume claim. There is a third abstraction, which is the storage class, which defines how it is possible to build a persistent volume, and it characterizes so the link between persistent volume claims and persistent volumes. In this lab, we use local persistent volumes, so those are simply bound to a node. They use the file system of a node. Those can be used mostly for testing purposes only. Those are not suitable for production workloads since they are strictly bound to a node, so we lose the possibility to schedule our workloads in any of the nodes of the cluster. For more production workloads, we typically leverage other solutions such as Ceph, NFS, or others, which build, let's say, an overlay storage continuum across all the nodes. So to start with just this simple test using the local persistent volumes, we need to first create our storage class. So once more, we have the storage class definition. It's the local one, and it says the volume binding mode is set to wait for first consumer. This means that it won't be created until a pod is actually being attached to a given piece of storage, so that it can take into account the additional constraints which are introduced by the fact that those are only present locally. So we create the storage class, okay, and then what we have to do is also to create a persistent volume. Here we are using once more the local persistent volumes, and those cannot be provisioned on demand as they are used mostly for testing, but need to be provisioned manually. Actually, it is also possible to add a controller to Kubernetes to make them be created automatically, but for the purpose of this test, it's fine to create them manually. So I should have a persistent volume definition. It says its capacity, so 1 GB in this case. The access mode, read-write once, means that we can access, only a single pod can access, be attached, and then access this persistent volume at any time. Here we reference the storage class that we created previously. We see the reclaim policy. How does it deal when we delete the persistent volume? we define additional parameters, additional information, in this case the path where it will be mounted, so on /data, and we set that this persistent volume will exist on the second worker, so on worker 2, by means of these node selector, node affinity and node selector expressions. So we create once more through kubectl apply our persistent volume. We can see it should have been created. Yeah, we have our local persistent volume, its capacity, it is available. It has not been bound to any pod. Now we have just to go a second to our worker. Let me copy. Okay. Let me copy the command. We need to go there. Hopefully, okay. We go there and just create the directory. This is once more because it's not done automatically. All these steps wouldn't have to be done if we used a more production grade solution. Let's say when you use Rook Ceph to provision persistent volume claims, you just create the persistent volume claim and then automatically the corresponding volume is provisioned and created in the underlying storage pool. So we completed our initial setup and we can go on. Here we have once more a deployment, in particular a Mysql deployment, which defines similarly to earlier our pod. We have a single container with a single replica that hosts MySQL, and here the difference is that we are referring to the volume, so we need to refer to a persistent volume claim, and we mount it into our container at this path. Additionally, we also changed the strategy type of the deployment to recreate. This is because if we want to update this deployment, we cannot create two replicas in parallel as usual. So one that is created, then it becomes ready, and the old one is terminated. This cannot be done as only a single pod can be bound to the persistent volume. So this tells the deployment controller, okay, first terminate the old pod and then create a new one, so that it is again possible to restart, to reattach the persistent volume claim. We also have, okay, we can start applying this one. If we check now the deployment, and in particular if we check the pod, we see that this remains pending, and this remains pending since we haven't created yet the persistent volume claim. So let's now see the persistent volume claim. We have a MySQL PVC file which defines the persistent volume claim, and in particular it targets once more the local storage, and it requests for 1 gig of data. So let's apply also it MySQL pvc.yaml. Now we have all the pieces in place. So we have a PVC which has been bound to our local PV, the persistent volume we created previously. So if we look at the persistent volume, we see that also it has been bound, and it has been bound to this to the persistent volume claim, and we can see that the pod is now running. We can also describe the pod MySQL. We see that it mounts the persistent volume, the persistent storage with this PVC claim name. Okay, so we have everything in place. What we can do now is access the pod, the MySQL pod, and see that effectively we can store data and this is preserved even if we stop the deployment. So let's access the pod. We use kubectl exec to exec into a pod. We specify the name of the pod, IT to attach the stream so that we can interact with the pod, and we specify the command that we want to execute, bin bash in this case. So we got a shell. Now the text of the lab suggests to log in into the MySQL database. The password is password. We actually configured here, and this is, by the way, not the best practice. We should leverage secrets to store, as the name says, secrets. But here, just for a test configuration, the password is hard-coded within the deployment. So we are now accessing our MySQL database, and we can, for instance, create a new database. We can show the databases, and effectively we have the pets database which has been created. So what we can do now is to exit. We can have a look at the pods. We delete the pod. Once more, we simulate a failure. But before deleting it, let's see one more thing. We can see with -o wide that the pod got scheduled on the worker 2, and this was a constraint since the volume is present only on that worker. So if we now delete the pod, okay, we see that it has been recreated. It has been recreated once more on the same node, since the storage is attracting our pod, and we can exec once more into our pod. Okay, the auto completion is not working, so let me copy it. Once more, we enter into the MySQL, and we can see now with show databases that our pets database is still present, since the database is saved on the persistent storage which is attached to our pod. So in this part you saw how we can create a simple stateful application and bind it to the to a piece of storage. Once more, this is not a production configuration, and the problem here is that if for any reason worker 2 is no longer available, let's say something wrong happens, the CPU dies, the RAM dies, whatever, you lose that node, you also lose the pod. Kubernetes won't be able to reschedule it on a different node, since it needs the piece of storage that is on that node. This problem isn't present when we use distributed storage solutions such as Rucksack. So this is everything for our for this part of the lab. So okay, probably I did something wrong. I wanted just to delete the deployments and the services, so that we can move on to the next parts. So just a brief introduction about what the other parts of the lab deal with, then you can explore them by yourself, and we can see in the lab and discuss if you have any question, any curiosity. So these the other parts of the lab deal with more advanced aspects of Kubernetes. The first deals with self-healing. So Kubernetes makes available some features such as readiness probes, liveness probes, to understand whether a pod is running correctly or not, so that it can be automatically restarted if it's not working properly. As we saw, pods are automatically recreated when they are deleted, but at the same time they are automatically recreated whenever the container within it crashes, or if some conditions, I was saying, some probe fails, and so that we can always be sure that our pods are running healthy. Another more advanced aspect in Kubernetes deals with resource allocation. So we now created some workloads, but we didn't specify any boundary in terms of the resources they can consume. And this can lead to different problems. The first one is that we are not setting any maximum. So if the pod starts behaving incorrectly, let's say starts consuming a lot of CPU and memory, it may damage our other workflows. At the same time, we are not reserving any resource amount for our workloads, so we are not guaranteed that there will be space in our cluster for them to run. So the typical approach is to specify, let me find the example, the resource boundaries in terms of requests and limits. Here you can see the two most common resources, so CPU and memory, but you can specify others. So limits are enforced by Kubernetes so that the application cannot go over those limits. In particular, with the limits in terms of CPU, it gets throttled. If it goes over the limits of the memory, it gets killed and restarted. While the requests are used by the scheduler to find the appropriate node to run these workloads, and are used so also to make it available to reserve those resources. In this part of the lab, you can also see more advanced features such as horizontal pod autoscaling, which is a feature that allows to automatically increase and decrease the number of replicas of a given deployment based on the current workload of that replica. So let's say if there is a lot of traffic, which in turn leads to high CPU consumption, the HPA will automatically increase the number of replicas. Conversely, if traffic goes low, so let's say the CPU consumption also goes low, then the number of replicas is reduced to save resources in the cluster. Finally, the lab will also allow you to experiment with permission management, so how you can give permissions, specific permissions to given users, either users or just system tokens which are assigned to the applications, so that you can specify who can do what to a pretty deep granularity, so allowing to specify for each resource which verbs, so which actions can be performed. Finally, you will also explore more in detail the exposition of applications, the one we talked previously, so the possibility to use ingress resources to expose applications by means of proxies. So the possibility to have, let's say for instance, an Nginx in front of your application which routes the traffic, which does SSL and TLS termination, and also all the jobs required to expose your applications to the external world. So that's everything for this video. Thank you for the attention and see you in the lab. Bye!